So the Fibonacci heap is a collection of trees with each tree following the minimum heap ordering property. Um, each tree root may have any degree, and the root list is not sorted by ascending order, unlike the binomial heap. Um, the heap maintains a pointer to the minimum element in the root list. Its siblings are connected through a circular doubly linked list, like here. There will be a pointer pointing from the head to the tail, and the tail will have a pointer pointing to its head. And a node in the heap will have a parent pointer, a child pointer, pointers to its left sibling and right sibling, a degree, which is the number of children of that node, data, and a mark value, which is a Boolean value indicating if its children have been deleted. Some standard functions of the Fibonacci heap include insert, find min, merge, extract min, decrease key, and delete. Insert simply adds a new node to the root list. There's no reordering, just attach and update the minimum pointer. That is done in constant time. Find min, since the heap tracks the smallest root, retrieving it takes O1 lookup. And for merge, it combines two heaps by linking their root lists together, again in O1 time. There are two phases in the extract min function. In the first phase, we remove the minimum element in the root list and merging its children into the root list. The second phase is consolidation. So in this Fibonacci heap, we remove 4 as the root list minimum element and merging the children. In the second phase, we have A as an array to store the node's degrees. We start at 24. 24 has a degree of 1, so we put that into A at index 1. 14 has a degree of 2, we put that into A at index 2, and we keep going until we encounter a node that has a degree that already exists in A, which is 23. 23 has a degree of 1, so we compare that with 24. 23 has a smaller key, so it becomes a new node, and 24 becomes its child. And we keep going until our root list has no duplicate degrees. There's no nodes with duplicate degrees, and this whole process takes O log n time. 2 degrees key of a node. First of all, we have 3 cases. The first case is that the node is smaller than its parent, and its parent is unmarked. We simply move the node and all of its children to the root list. The second case is where the node is smaller than its parent and the parent is marked. In that case, first we move the node into the root list, and the parent, we also move the parent to the root list, and then we unmark the parent after it's moved to the root list, and we check for its parent's parent to see if it's marked, and if it's marked, we also move its parent, including as well as all of its children, to the root list and unmark it. So we keep repeating this process until we've reached a parent that is unmarked, or if we've reached the root list. So in the first case, that would be O1 time complexity. In the second case, because we have to iterate through, in the worst case, the entire height of the tree, that would take O log n, with n being the number of vertices. So here, as a demonstration, we have 23. 23 is smaller than 29. 29 is not marked, so we move 23 to the root list here. In the second case, we try changing 66 to 4. So we move this entire subtree into the root list, and then we see that 59 is marked, so we also move 59 into the root list, and then 28 is the parent of 59 is also marked, so we move this entire subtree into the root list and unmark it. So that's for decrease key. For delete node, first there are 2 phases. First, we decrease the key of the node that we want to delete into the smallest value, into the smallest key, and then we perform decrease key that would take that node and its children to the root list, and from there we perform extract min. Obviously, extract min and decrease key have O log n, worst case time complexity. So for delete node, the worst case time complexity would be also O log n. In summary, the Fibonacci heap is a specialized priority queue data structure. It solves the main goal of minimizing the time complexity of the decrease key operation. Other structures like the binary heap take O log n time for this operation, and the Fibonacci heap only takes O1 amortized time. And theoretically, this makes it the go-to choice for algorithms that rely on key reductions, like the standard implementations of Dijkstra's shortest path and Prim's minimum spanning tree. It has some limitations, such as this complex structure that requires many pointers and flags, leading to high constant factors. So in practice, simpler heaps like the binary or pairing heaps are often faster for common use cases. It's also difficult to implement in a sense that each layer of its children are a cycle W linked list. The interesting part of it is that its laziness, basically it postpones the costly structural cleanup until the delete min operation instead of fixing the heap right after every change. This laziness is what allows for the O1 amortized time for both insertion and decrease key. Its structure's properties are mathematically linked to the Fibonacci numbers, giving the heap its name.